Hi, today I will tell you how to get the gene names in your results table if they are missing. I will continue the same example as I did before. This is the GEC number for microarray expression data taken from NCBI geosite, and you do all the standard options and generate the script on the R script page, which you copy and paste to your RStudio. After you copy paste the script to the RStudio, you have to save it. You give some clear name, what it is, where it's from. This is original version without any changes or modifications. And I previously told you that I prefer to do modifications and simplifications. And then I save it as a different file name. Please note that RStudio does not automatically save all your changes. You have to save it yourself. Click on this button or go to menu, file, save as, and preferably you give every time you make major changes, you give a different name and make a different copy. And modifications which I did were good enough to have a differential expression table, but it had no gene names as we used to, and therefore I did a further modification in the third version of the script, which has this part where to get those names and how to add them to your table. Let's go briefly through the script. So you import GeoQuery and Lima. You don't import UMAP. You keep this part as there are in original the script. The expression part can be called using XPRS gset. Before that you have to decide, and I forgot it, whether you have to do log transform or not. For this you call the box plot. You don't care much about annotations yet. You simply check this scale and see that it is a small scale. It's from 2 to 12. It's a small size. It's not in the hundreds, and boxes are symmetrical. Very likely, it is already log transformed. That's a feature of log transform data. Before that, you can also say hist, and you have it do it as matrix. Then you get all the data on the histogram. And then again you have this typical log transformed profile with the two peaks. This is about zero intensities, and these are true hybridization signal intensities. Both those figures indicate that your data are already log transformed, and the whole essence of log transformation is not that you need the small numbers, but you have to get data distribution close to normally distributed data. That's the idea. And then talking about normally distributed data, we still do a normalization, which has nothing to do with the data distribution. It has to do with making the boxes equal. Quantile normalization makes them absolutely equal. So you do it. Then, as I told you, what I prefer to do, I extract sample information out of gset using this address. Details you will see in the previous video. And I also now declare it as a data frame, because otherwise it will complain. I give row names and column names because they were spoiled during the string split operation. And I also add one more column to the samples table. Why? Because using groups column, you can select wild type old against wild type young and have exactly the same groups of comparison what you did online in our previous video. But of course you can manipulate with this sample table, so you can call design as a comparison of groups, or you can select a column cells in the same sample table, this one, compare wild type with the LNK mutant, or you can compare ages, old and young, but note that if you compare ages alone, that wild type and LNK mutant will form one group. And if you compare, take a groups table, then you have a possibility to take them in separate. So there will be 4 groups, not 2. But it's up to you what you do. And you can also combine cells and age. There is nothing wrong with the combining multiple columns. And you put first what is your primary interest, and later components will be used as a correction factor. So you will get better results what is really dependent on the cells and corrected by age and other things. That's the trick. And then we go on and say fit, and then check the fit. What's the names? That's are the names which I copy paste into contrasts matrix and do fit again by the contrast, and then do statistics and generate top table. Then I check call names in a top table, and my preference is such that I do not see much point of keeping b values or p-value next to adjusted p-value or t-value. They are pretty meaningless as an end product. I would better add columns ID and trace gene ID. I need it for further gene annotation, description what gene does, log fold change, average expression, and adjusted p-value. These are all useful columns in my table. And you can always click and see what it is. So the gene names are missing. We have microarray numbers, interest gene numbers, gene description, but no names yet. And of course later we have log FC expression, adjust p-value. That's useful stuff. So then we generate the tops. There are 2 alternatives declaring tops. It's equivalent expression. You either say top table where adjusted p-value less than 0.005, comma, saying that get it by rows. Or you can say tops is a subset of top table where adjusted p-value is less than 0.005. You use either of those 2 and it will be enough. And here you see 584 genes are selected, and if you do this again 584 genes are selected. And now we come to the annotation business. So there are 2 ways of doing it. First, you have a small library in a Bioconductor, relatively small. So you call AnnotationDbi for functionality, org-mm egdb, that's the data source. And if you are with a human, then instead of which is abbreviation for mouse, you type here HS, Homo sapiens, and the rest is the same. So you call those two. Then you can inquire what does it have for you, and it says if you're interested in gene annotation, these are the categories available. Among those is entries ID is available, which is also available in our tops. And this is what you use in defining your anno file, that you say give me entries IDs and gene symbol. Symbol is for gene symbol out of database. It does. And then you also ask that the selection key is entries ID in your tops table, and then immediately gives exactly the same number of annotations out of the database. You can have a look. So that's entries ID, that's the symbol which you was missing. And so the remaining part is simply merge those two tables together, and you do it with the function merge. And then this is the end product, which you can save as a write CSV and merged, and the name and so on. All the details you can exercise yourself. The merge function can merge two tables in one if both of the tables, like this for instance and that, contain a column with the common elements. In this particular example, you have a column 1 in table 1 ABC, and in table 2 you have a BAC. So you have to indicate for merge function that column 1 in table 1 and column 1 in table 2 are columns used for a merger, and the function will generate the final table of 3 columns. It will not repeat this common column twice, it will make it only once, and merge all other columns in the right order, in a relevant order to the column which you use for a merger. That's the trick. Now option number 2, using biomaRt. biomaRt is an online database touch to ensemble, and it actually supports ensemble pages. If you come here, you can do it manually and select and find all the information about genes in mouse, human, chicken, rat, zebrafish, and lots of more. It's very big. In our particular case, we select mouse, we skip filters. You can filter for different kinds of genes. We only need attributes, for instance, gene ID, gene name, and you can select more. I could not find entries IDs. There is entries gene transcript name, but it's different. Anyway, in this case you do not have R script but Perl script on the back of this selector. And what is important and tells you, in cases you don't know, the names of identifiers which you will need for your communication with the biomaRt in R. In order to communicate with the biomaRt, you have to call biomaRt library. Then you call ensemble ensemble biomaRt dataset mus musculus gene ensemble. This name you can see already in biomaRt after you select a database there. Before that, I think I use a selection. And now I am calling biomaRt and say give me the entries gene IDs for my selection of genes. And then I check the size of it, and here is a problem that if you communicate to biomaRt, unlike to org-mm, you find less annotated genes. Why it is, I don't know, but it means that you cannot simply merge those two data tables because they have different size, and so you have to chop your tops, create, so to say, tops 3, where you select only those lines which are in a annotation file of biomaRt. And after this reduction, you merge. Now they are equal size. And the same story. You can then delete some columns if you don't want them. Simply saying, for instance, 3 is say -1 column, so then the first column will be removed. All with the minus will be removed. This column is gone. You can also remove ID, but it's all up to you. I give you idea what it is. And so we come to the end